Hi students, in this class we are going to study the modeling of medium length transmission lines. We will study the nominal T method. Mr. Alex is working in a popular hotel. He serves coffee to the customers. He has one bad quality. Usually he takes a couple of sips before the coffee is being served to the customer. The hotel people are well aware of this bad quality of Mr. Alex. Actually, the customer needs 150 ml of coffee. Mr. Alex takes some 25 ml of coffee. So usually the coffee maker pours some 175 ml of coffee to Mr. Alex's jug. So the customer will get exactly 150 ml of coffee. And he is happy as long as he doesn't know the matter. The scenario is similar in the case of transmission lines. Suppose the consumer needs some 11 kilovolt at the load center. How much voltage should be produced at the generator? Because the transmission network will take certain amount of voltage. For that, we should know the structure of the transmission line, or we should know the characteristics of the transmission network. That's why we study the modeling of transmission lines. Based on the length and operating voltage, we can classify the transmission lines into short, medium and long transmission lines. And in this class, we are going to study the medium transmission lines. When you model the medium transmission lines, we have to consider the effect of capacitance of transmission lines. And based on the location of the capacitor where it is placed, we can classify the modeling into N-condenser method, nominal T and nominal pi method. This classification is based on the position of the capacitor, whether it is at the end, as in the case of N-condenser method, or at the middle, that is the case with the nominal T method, and in the nominal pi, both at the sending end and at the receiving end, we have capacitors. In this class, we are going to study the nominal T method. Let me draw the equivalent circuit of a three-phase transmission line. Actually, we consider only one phase because we assume that the three-phase system is balanced. So analysis of one phase is enough here. We assume that the capacitor is placed at the middle of the line. This is the position of the capacitor. This is the sending end voltage. The capacitor is placed at the middle. The resistors and the reactors are equally divided between the two sides of the transmission line. The capacitor is placed at the middle of the line in the case of nominal T method. And this is the load. Half of the resistance is placed on the left side of the line. Half the resistance is placed on the right side of the line. Half the reactance on the left side. Half the reactance on the right side. The receiving end voltage is VR. The sending end voltage is Vs. The voltage across this capacitor is taken as V1. The receiving end current is IR. The current through this capacitor is IC. So the sending end current IS is equal to IC plus IR. Now we have to find out Vs from the knowledge of VR. First we will find out V1. So V1 can be written as VR plus the current into this impedance, or VR plus this drop will give V1. All are vector quantities. Psi R into R by 2 plus IR into XL by 2. This is V1. From V1 we should find out Vs. Vs is equal to V1 plus the drop in this part of the line, where the current is Is, into the drop across the resistor plus the drop across the inductor. So this is how we are going to find out the sending end voltage. First we will find out V1, voltage across the capacitor. From that we will find out Vs. Now let me draw the phasor diagram. We take VR as the reference vector. The receiving end voltage is taken as the reference vector, so it is drawn horizontally. Suppose this is the receiving end current IR. It lags behind the voltage by an angle phi r. So this is the receiving end phase angle. Now we are going to find out V1 first. V1 is equal to the receiving end voltage plus the drop in this part of the line. So it is VR plus, we have two drops. One is the drop across the resistor, then the second is the drop across this inductor. The drop across the resistor should be drawn in parallel with the current, because in the case of resistors both voltage and current are in phase. Here the voltage drop is IR into R by 2. So this is drawn in parallel with IR. Next is the drop across the inductor. As you know, in the case of inductors, if this is the voltage, the current lags behind the voltage by 90 degrees, or I can say the voltage leads the current by 90 degrees. So this is the direction of current, so the voltage should lead the current by 90 degrees. So this is IR into XL by 2. This is the direction of current, so the voltage leads the current by 90 degrees. Here the sum is V1. So V1 is equal to VR plus the drop across the resistor plus the drop across the inductor. This can also be drawn as IR into Z by 2. So we got V1. Now from this we are going to find out Vs. Voltage across the capacitor is V1. The current is IC. And this current should lead the voltage by 90 degrees, because in the case of capacitors, if this is the voltage, current leads the voltage by 90 degrees. Where the voltage across the capacitor is V1, this is the voltage. So current should be in this direction. Current should lead the voltage by 90 degrees. So this is IC, the current flowing through the capacitor. and IR plus IC is equal to IS. So this is IS. This is the sending end current, which is equal to the receiving end current plus the capacitor current. IS is equal to IR plus IC. We got V1. Now we have to find out Vs. Vs is equal to V1 plus the drop across the resistor plus the drop across the inductor. This is V1. The drop across the resistor should be in phase with the current. This is the direction of current IS. So the voltage across the resistor should be drawn in the direction of IS. This is the voltage across the resistor. It is current into resistance. That should be in phase with the current IS. Next is the drop across the this inductor. As you know, the voltage across the inductor leads the current by 90 degrees. Where the voltage drop is IS into XL by 2. This is our resultant vector. V1 plus the drop across this resistor plus the drop across the inductor will give Vs. So this is Vs. And this can also be represented as IS into Z by 2. So from this we can write Vs is equal to VR plus polar vectors IR into Z by 2 is the drop on the right side of the line plus IS into Z by 2. This is the drop on the left side of the line. So from this expression we can find out the sending end voltage Vs.